Hello and welcome to Moonlit Physics. Before we begin tonight's journey, take a moment to like the video and subscribe to the channel if you enjoy calm explorations of space, physics, and the quiet forces that shape our universe. And I'd love to know, where are you watching or listening from tonight? Perhaps you're near a coastline where the tide is slowly rising or falling right now. Or maybe you're far inland, hundreds or even thousands of kilometers from the ocean, where the moon is still quietly moving the water all the same. Because whether we notice it or not, the oceans of Earth are constantly in motion. Every hour of every day, vast masses of seawater are gently shifting across the surface of our planet. Coastlines slowly reveal wet sand and then hide it again. Harbours rise and fall. Entire bays inhale and exhale, with a rhythm so steady that sailors have trusted it for centuries. But the remarkable thing is this. These enormous movements of water are not driven by wind, not by storms, and not by the restless energy of the oceans themselves. Instead, they are guided by something much farther away. Roughly 384,000 kilometers above us, the moon is silently exerting its influence on Earth. Its gravity reaches across space and subtly reshapes our oceans, pulling and stretching them in ways that create the tides we experience along every shoreline on the planet. It's a quiet interaction, almost imperceptible moment to moment, and yet it moves billions of tons of water every single day. For thousands of years, people noticed the pattern. Fishermen, navigators, and coastal communities learned that the sea followed the moon. When the moon was full, tides behaved differently. When the moon was new, the ocean seemed to respond again. But for a long time, no one truly understood why. How could an object so distant influence something as vast as the oceans? Why does the water rise twice each day instead of once? And why does the ocean bulge not only toward the moon, but also on the opposite side of the planet? The answers to these questions would eventually lead scientists into some of the deepest ideas in physics: gravity, orbital motion, planetary mechanics, and even the curvature of space itself. Tonight, we're going to explore that story slowly. We'll begin with the oceans themselves, this thin, restless layer of water that covers most of our planet. Then we'll look upward, toward the moon, and discover how its gravitational pull reshapes the oceans in ways that are both simple and profoundly elegant. Along the way, we'll explore ideas developed by scientists across centuries. From early observers who first noticed the moon's connection to the sea, to mathematicians who uncovered the physics of tides, to modern researchers who study tidal forces not only on Earth, but across the entire solar system, and even beyond. Because the gentle rise and fall of the ocean is not just an earthly phenomenon. It's part of a much larger cosmic story, a story about gravity, motion, and the quiet dance between two celestial bodies that have been influencing each other for more than 4 billion years. So wherever you are tonight, whether you're listening beside the sea, in a city far from the coast, or somewhere inland where the tides are invisible but still very real, settle in. And let's explore a simple but fascinating question. Why does the moon move the oceans? If you were standing beside the ocean long enough, you would begin to notice something quietly remarkable. The shoreline does not stay still. Over the course of the day, the sea slowly creeps forward, covering rocks and sand that were dry only hours before. Later it withdraws again, revealing shells, seaweed, and small pools of trapped water glistening in the light. Nothing about this motion feels hurried. It is gradual, patient, almost breathing in its rhythm. This steady rising and falling of the sea is known as the tide. Unlike waves, which are stirred by winds sweeping across the surface, tides unfold slowly and predictably. Their motion can take hours. Entire coastlines participate in the movement, sometimes lifting or lowering the ocean by several meters. In some places, the change is gentle, barely noticeable unless you watch carefully. In other locations, the transformation is dramatic. Consider the Bay of Fundy in eastern Canada, where the difference between high tide and low tide can reach more than 15 meters. During low tide, fishing boats rest on the muddy seabed. A few hours later, those same boats float high above the harbour floor as the ocean returns. What makes this even more remarkable is that this immense movement of water happens not just in one bay or one country, but across the entire planet. Every day, vast portions of Earth's oceans shift position in a slow and deliberate cycle. Billions upon billions of tons of seawater rise and fall, responding to forces that are invisible, yet extraordinarily powerful. And yet for most of human history, people simply accepted the tides as a fact of coastal life. Fishermen learned when to launch their boats, harbour masters knew when ships could safely enter shallow channels, communities built their routines around the reliable advance and retreat of the sea. Tides determined when fishing nets were set, when shellfish could be gathered, and when coastal passage was safe. Long before modern science, the rhythms of the ocean were already guiding human activity. Ancient sailors of the Mediterranean carefully observed the sea's changing levels. In parts of northern Europe, coastal communities noticed that the tides followed a pattern connected to the phases of the moon. When the moon was full, the ocean seemed to behave differently. When it disappeared during the new moon, the water changed again. These observations were not subtle. Anyone living near the sea for long enough could see the connection. Yet the explanation remained mysterious. How could the moon, a silent object hanging high in the sky, influence the immense weight of Earth's oceans? To appreciate the scale of the puzzle, it helps to think about the mass involved. The oceans contain roughly 1.3 billion cubic kilometers of water. Even small shifts in ocean height represent an enormous redistribution of matter across the surface of the planet. Moving such quantities of water would seem to require tremendous energy. And yet the tides unfold quietly. There are no roaring engines driving the process, no storms pushing the water forward. The motion happens even on perfectly calm days, when the surface of the sea looks like polished glass. Something else must be responsible. The answer, as it turns out, lies not in the ocean itself, but in the invisible architecture of the universe. The tides are driven by gravity. Gravity is the interaction that causes objects with mass to attract one another. It is the same force that keeps the moon in orbit around Earth and the Earth in orbit around the sun. Every object with mass exerts gravitational influence on other objects. Even you, sitting where you are right now, exert a tiny gravitational pull on the chair beneath you. The effect is extraordinarily small, of course, but the principle is the same. When it comes to celestial bodies, however, gravity becomes powerful enough to shape entire worlds. The moon, despite being much smaller than Earth, still possesses significant mass. That mass creates a gravitational field that extends far out into space, reaching across the distance that separates the moon from our planet. That distance is roughly 384,000 kilometers. Across that vast stretch of space, the moon's gravity interacts with Earth. It pulls on the planet itself, it pulls on the atmosphere, and most noticeably it pulls on the oceans. But the way this pull works is not quite what intuition might suggest. The moon does not simply drag the oceans toward it like a magnet lifting iron filings. If that were the case, the tides would behave very differently from what we observe. Instead, the true mechanism involves something more subtle and more fascinating. The moon's gravity pulls on different parts of Earth, with slightly different strength. The side of Earth that faces the moon is a little closer to it, so the gravitational attraction there is slightly stronger. The opposite side of Earth is slightly farther away, so the gravitational pull is slightly weaker. This tiny difference in gravitational strength across the diameter of our planet produces what scientists call a tidal force. The concept was first explained mathematically in the late 17th century by the English physicist Isaac Newton. In his groundbreaking work titled Philosophiae Naturalis Principia Mathematica, published in 1687, Newton described gravity as a universal interaction acting between all masses in the universe. Using his law of universal gravitation, Newton demonstrated that the gravitational force between two objects depends on their masses and the distance between them. In simple terms, larger masses create stronger gravitational attraction, while greater distances weaken the effect. The equation describing this relationship is often expressed as force equals the gravitational constant multiplied by the mass of the first object, multiplied by the mass of the second object divided by the square of the distance between their centers. This principle provided the first clear scientific explanation for the tides. Later scientists refined Newton's ideas. The French mathematician Pierre-Simon Laplace developed sophisticated tidal equations in the late 1800s that allowed scientists to model how ocean basins respond to gravitational forces. Oceanographers such as Joseph Proudman and Henry Stommel would continue this work in the 20th century, helping to explain the complex patterns of tides across different parts of the world. But the central insight remains elegantly simple. The tides are not driven by wind. They are not driven by temperature. They are not even driven primarily by processes happening within the oceans themselves. Instead, the tides are a direct consequence of the gravitational relationship between Earth and the Moon. Every hour, every day, the Moon's gravity gently reshapes the oceans. It stretches the water slightly toward itself, while the rotation of the Earth carries coastlines through these shifting ocean bulges. The result is the slow, rhythmic rise and fall of the sea. It is easy to overlook this motion because it unfolds so gradually. Yet when viewed from a planetary perspective, the tides represent one of the largest continuous movements of matter occurring on Earth. The oceans are responding to a distant companion in space. And this quiet gravitational conversation between Earth and the Moon has been ongoing for more than 4 billion years. From space, Earth has a distinctive appearance that immediately sets it apart from the other rocky worlds of the solar system. Most planets with solid surfaces are dominated by stone, dust, and deserts of frozen or volcanic terrain. Mars is rust-coloured and dry. Mercury is scarred by craters. Even Venus, though wrapped in thick clouds, hides a landscape of lava plains beneath its atmosphere. Earth, by contrast, shines blue. Astronauts orbiting the planet often describe the same first impression. Looking down from orbit, the most striking feature is not land, but water. Vast expanses of deep blue stretch across the surface, broken only by the shapes of continents and drifting white cloud systems. This is because the oceans cover roughly 71% of Earth's surface. That proportion is enormous. Imagine dividing the entire surface of the planet into 10 equal parts. More than 7 of those parts would be covered by ocean, leaving less than 3 parts for all the continents, islands, mountains, forests, cities, and deserts combined. The result is that Earth is not simply a rocky planet with some water on it. In many ways, it is more accurate to think of Earth as a water world with scattered continents rising above the surface. These oceans are also astonishing in scale. The total volume of seawater on Earth is roughly 1.3 billion cubic kilometers. If you could somehow gather all of that water into a single sphere, it would form a globe more than 1,400 kilometers across. Of course, that is not how the water is arranged. Instead, the oceans form a thin layer spread across the surface of the planet. Compared with the size of Earth itself, the oceans are surprisingly shallow. The average ocean depth is around 3,700 meters, which is only a small fraction of Earth's radius of about 6,300 kilometers. If Earth were scaled down to the size of a basketball, the oceans would be thinner than the thickness of its paint. Yet despite being thin on a planetary scale, the oceans behave in powerful and dynamic ways. Water is a fluid, meaning it flows easily and responds quickly to forces acting upon it. Unlike the solid crust of the planet, which resists deformation, seawater can move, shift, and redistribute itself across enormous distances. In effect, the oceans form a continuous fluid shell wrapped around the planet, and that shell is constantly moving. Some of that motion occurs at the surface. Winds blowing across the sea generate waves and push water into large rotating currents known as gyres. Ocean currents such as the Gulf Stream transport heat across entire oceans, helping regulate Earth's climate. But not all ocean motion is driven by the atmosphere. Deep beneath the surface, water slowly circulates through complex patterns known as thermohaline circulation. This global conveyor belt of seawater is driven by differences in temperature and salinity. Cold, dense water sinks near the polar regions and gradually flows through the depths of the oceans before rising again elsewhere. Oceanographers often describe this process as a planetary scale circulation system that takes hundreds or even thousands of years to complete a full cycle. Yet even these vast currents are not the motion we are focusing on here. Tides are something different. When the tide rises along a coastline, the ocean does not simply pile up water in one location like waves crashing onto the beach. Instead, the entire ocean basin responds. Water shifts across enormous distances as the shape of the ocean surface changes very slightly. One way to imagine this is to picture the oceans as a flexible layer covering a spinning sphere. When forces act upon that layer, the water redistributes itself. Some regions experience a slight increase in ocean height, while other regions experience a corresponding decrease. The total amount of water remains the same, but its distribution changes. This is why scientists often describe tides as a planetary scale redistribution of ocean mass. At any given moment, enormous regions of the ocean surface are slightly elevated, forming broad bulges of water, Other regions are slightly lower. As Earth rotates beneath these shifting bulges, coastlines pass through areas of higher and lower sea level. To someone standing on shore, the effect appears as the familiar cycle of rising and falling tides. What is important to understand is that this process involves the entire ocean system. The Pacific Ocean, the Atlantic Ocean, the Indian Ocean, the Southern Ocean, and the Arctic Ocean are often spoken of as separate bodies of water. In reality, they are all connected. Water can flow between them through straits and passages. On a planetary scale, the oceans behave as one continuous global system. Because of this connectivity, forces acting on one region of the ocean can influence water movement thousands of kilometers away. The geometry of the ocean basins also plays an important role. Continents interrupt the flow of water and shape the paths along which tidal waves travel. Narrow channels can amplify tidal motion, while broad open basins may spread the movement over larger areas. Oceanographers such as Joseph Proudman and later Henry Stommel spent much of the 20th century studying how the shape of the seafloor and the arrangement of continents influence ocean circulation and tidal patterns. Yet even when all these factors are taken into account, one question remains central. What force is powerful enough to influence the oceans on a global scale? Wind can move water locally, but winds change constantly and rarely act with the precision needed to produce such regular cycles. Temperature differences can drive deep currents, but those processes unfold over decades or centuries rather than hours. The tides follow a far more reliable schedule. High tide arrives, the water slowly retreats, and then the ocean returns again. This cycle repeats day after day with remarkable consistency. In fact, the timing of tides can be predicted with impressive accuracy years in advance. Such regularity hints at something fundamental. In science, when a pattern repeats with clock-like precision, the cause is often astronomical. Astronomical motions, such as the rotation of Earth or the orbit of the Moon, occur with extraordinary stability. These celestial movements provide some of the most reliable rhythms in nature. The key insight, first recognized centuries ago, is that the oceans are not moving solely because of processes happening on Earth. They are responding to gravitational influences originating beyond the planet. Somewhere above our heads, an object is exerting a subtle but persistent pull on the oceans. That pull stretches the global ocean slightly out of shape, creating regions where water gathers and regions where it thins. As the planet turns beneath this shifting pattern, coastlines experience the steady rise and fall we call the tides. To understand how this works, we must now look beyond the oceans themselves. We must look outward, toward the celestial companion that has been shaping Earth's waters for billions of years, the Moon. To understand why the Moon can move the oceans, we first need to understand the quiet force that governs nearly every large movement in the universe. That force is gravity. Gravity is the interaction that causes objects with mass to attract one another. It is responsible for keeping the Moon in orbit around Earth, the Earth in orbit around the Sun, and the Sun itself moving through the vast structure of our galaxy. Without gravity, planets would drift away into empty space. Stars would never form. Galaxies would never gather their billions of suns together. Even the air you breathe and the water in the oceans would not remain attached to Earth. Gravity, in a sense, is the cosmic glue that shapes the large-scale architecture of the universe. What makes gravity particularly fascinating is that it operates everywhere. Every object with mass generates gravitational influence. The Earth pulls on you, which is why your feet remain on the ground. At the same time, you pull on the Earth as well. The difference is that Earth is unimaginably massive compared with a human being. Our planet has a mass of roughly 6 septillion kilograms. That is 6 followed by 24 zeros. Because gravitational strength depends on mass, the Earth's pull on you is vastly stronger than your pull on Earth. The same idea applies to celestial bodies. The Moon pulls on the Earth pulls on the Moon, the Sun pulls on both of them. Every object in the universe participates in this quiet exchange of gravitational influence. The first person to describe this interaction in a precise mathematical way was the English scientist Isaac Newton. Newton was born in 1642, during a time when scientists were beginning to understand the motion of the heavens in a new and more rigorous way. Earlier astronomers such as Johannes Kepler had already discovered that planets move in elliptical orbits around the Sun, but the deeper reason behind that motion was still unknown. Newton's great insight was that the same force causing an apple to fall from a tree might also be responsible for holding the moon in orbit around Earth. He developed a theory known as the law of universal gravitation. The word universal was important because Newton believed the law applied everywhere in the cosmos, not just on Earth. The law can be expressed in a simple relationship. The gravitational force between two objects depends on their masses and the distance between them. In words, the relationship can be described as follows. Force equals the gravitational constant multiplied by the mass of the first object, multiplied by the mass of the second object, divided by the square of the distance between their centers. Although the equation itself is compact, its implications are profound. It tells us that larger objects exert stronger gravitational attraction. It also tells us that the strength of gravity decreases rapidly as distance increases. If the distance between two objects doubles, the gravitational force between them becomes 4 times weaker. This principle explains why the Moon, despite being much smaller than Earth, can still influence our planet. The Moon's mass is enormous on human scales, roughly 73 sextillion kilograms. Even across the vast distance separating it from Earth, its gravity remains strong enough to affect our planet. Newton's theory worked remarkably well. It could predict the motion of planets, calculate the paths of comets, and explain why objects fall toward Earth. But Newton himself was uneasy about one aspect of his theory. His equations described how gravity behaved, yet they did not explain how gravity actually worked. How could two objects influence each other across empty space? What mechanism allowed the Earth to pull on the Moon when nothing visible connected them? For centuries this question lingered. A different perspective began to emerge in the 19th century through the work of the English scientist Michael Faraday. Faraday was one of the great experimental physicists in history. He conducted groundbreaking research into electricity and magnetism, discovering how electric currents could create magnetic fields and how magnetic fields could generate electricity. In studying these phenomena, Faraday developed an idea known as the field concept. Rather than imagining forces acting instantly across empty space, Faraday proposed that objects create fields around themselves. These fields fill the surrounding space and influence other objects that enter them. For example, a magnet produces a magnetic field that extends outward in all directions. Another magnet placed within that field will feel a force because it is interacting with the structure of the field itself. Faraday suggested that gravity might operate in a similar way. Although he did not fully develop the mathematical theory, his idea that space could contain invisible fields would later become central to modern physics. Faraday's insights strongly influenced another towering figure of 19th century science, the Scottish physicist James Clerk Maxwell. Maxwell unified electricity and magnetism into a single theory known as electromagnetism. His equations described how electric and magnetic fields behave and how they travel through space as waves. Maxwell's work demonstrated that fields were not just abstract concepts. They were real physical structures capable of carrying energy and information across the universe. These developments set the stage for an even deeper understanding of gravity in the early 20th century. In 1915, the German physicist Albert Einstein introduced the general theory of relativity. This theory completely transformed the scientific view of gravity. Instead of describing gravity as a force pulling objects toward one another, Einstein proposed something far more subtle. According to general relativity, mass and energy warp the fabric of space and time itself. A useful way to visualize this idea is to imagine space as a flexible surface. When a massive object such as a planet or star sits within that surface, it creates a depression or curvature. Other objects moving nearby follow paths shaped by that curvature. In Einstein's view, the Earth does not orbit the Sun because the Sun is pulling on it with a mysterious force. Instead, the Earth moves along the curved geometry of space-time created by the Sun's mass. The same principle applies to the Moon and the Earth. The Moon alters the geometry of space-time in the region around it. Earth moves through that curved space-time, and the oceans respond to the subtle differences in gravitational influence across the planet. This brings us directly to the phenomenon that produces tides. Tidal forces arise because gravity does not act equally across large objects. The side of Earth that faces the Moon is slightly closer to it. Because gravitational strength increases with proximity, the Moon pulls more strongly on that near side. Meanwhile, the far side of Earth is slightly farther away from the Moon, and therefore experiences a slightly weaker pull. The difference between these two gravitational influences is small, but it is extremely important. Across the 12,700 kilometer diameter of Earth, the variation in gravitational strength creates a stretching effect. The planet and its oceans are pulled slightly toward the Moon on one side and slightly away on the other. This difference in gravitational influence is the essence of tidal force. The oceans, being fluid and mobile, respond more easily to this stretching than the solid crust of the Earth. Water shifts across the surface of the planet, forming subtle bulges in the ocean surface. As Earth rotates beneath these shifting bulges, coastlines experience the rising and falling of the sea that we know as the tides. What appears to us as a simple daily rhythm of water along the shore is therefore rooted in one of the deepest ideas in physics. Gravity, acting across space, quietly reshapes the oceans of an entire planet. To understand why the Moon has such a powerful influence on Earth's oceans, it helps to begin much earlier in the story, long before tides existed, long before the oceans even formed. The Earth and the Moon were not always companions in the quiet partnership we see today. Their relationship began in an event so violent that it reshaped the entire young planet. Scientists now believe that the Moon was born from a colossal collision that took place more than 4 billion years ago. The leading explanation for this event is known as the giant impact hypothesis, a theory that has become the dominant model for lunar formation. The foundations of this idea were developed in the mid-1970s by planetary scientists William Hartmann and Donald Davis. At the time, researchers were trying to solve a puzzle that had troubled astronomers for decades. The Moon seemed both similar to Earth and strangely different at the same time. Samples brought back by the Apollo missions revealed that lunar rocks share many chemical similarities with Earth's mantle, the thick layer of rock beneath our planet's crust. Yet the Moon also lacks large amounts of iron compared with Earth's core. This combination of similarities and differences suggested that the Moon did not form independently somewhere else in the solar system, and later become captured by Earth's gravity. Instead, the evidence pointed toward a shared origin. Hartmann and Davis proposed a dramatic explanation. In the early solar system, planets were still forming from a swirling disk of dust, rock, and gas surrounding the young sun. The environment was chaotic. Newly forming worlds frequently collided with one another as their orbits evolved. During this turbulent era, Earth itself was still growing. It had not yet settled into the stable planet we know today. According to the giant impact hypothesis, a large protoplanet roughly the size of Mars collided with the young Earth. This object is often given the name Theia, after a figure from Greek mythology who was the mother of the moon goddess Selene. The collision was not a gentle encounter. It was an impact of unimaginable scale. At the moment of contact, enormous amounts of energy were released. Rock from both bodies vaporized. Vast quantities of molten material were blasted outward into space. Computer simulations performed by planetary scientists at institutions such as the Southwest Research Institute and the University of California have helped scientists visualize how such an event might have unfolded. In these models, the impact does not completely destroy Earth. Instead, the collision partially melts the outer layers of the planet while ejecting an enormous cloud of debris into orbit. This debris forms a glowing ring of rock vapor and molten fragments surrounding Earth. Over time, gravity begins to gather this material together. Small clumps merge into larger ones. Larger fragments collide and stick together, gradually forming a single growing body. Within a relatively short astronomical timescale, perhaps only a few thousand years, this orbiting debris coalesces into the Moon. The result is the Earth-Moon system we recognize today. What makes this origin story particularly compelling is how well it explains the properties of the Moon. Because much of the debris came from Earth's outer layers rather than its iron-rich core, the Moon ended up with a relatively small metallic core of its own. This matches the measurements scientists have made using seismic instruments placed on the Moon by Apollo astronauts. The theory also explains why lunar rocks have chemical compositions so similar to those of Earth's mantle. They were born from the same material. The giant impact hypothesis has been refined over the decades through detailed modelling and geochemical studies. Research groups around the world, including teams at NASA and the Lunar and Planetary Institute in Texas, continue to explore the exact details of the collision. Yet the central idea remains widely accepted among planetary scientists. The Moon was born from Earth, but the importance of that ancient collision goes far beyond the creation of a satellite. The presence of the Moon profoundly shaped the long-term evolution of our planet. Immediately after the impact, the Moon would have been far closer to Earth than it is today. Some estimates suggest it may have orbited at a distance of only 20,000 to 30,000 kilometers. At that distance, the Moon would have appeared enormous in the sky, several times larger than the Moon we see now. More importantly, its gravitational influence would have been dramatically stronger. As the Moon orbited the young Earth, gravitational forces began to reshape both bodies. The newly formed Moon gradually moved outward as energy was transferred between the Earth's rotation and the Moon's orbit. This process continues even today, though at a very slow pace. Modern measurements using laser reflectors left on the Moon by Apollo astronauts have shown that the Moon is slowly drifting away from Earth at a rate of about 3.8 centimeters per year. That distance may seem tiny, roughly the speed at which human fingernails grow, but over millions of years the change becomes significant. Long ago, when the Moon was closer, tidal forces on Earth would have been far stronger than they are today. Those forces did not only affect the oceans, they influenced Earth's rotation, its climate stability, and possibly even the early conditions that allowed life to develop. One particularly important effect involves the tilt of Earth's rotational axis. Our planet is tilted by about 23.5 degrees relative to its orbit around the Sun. This tilt is what produces the seasons. Without the stabilizing gravitational influence of the Moon, computer simulations suggest that Earth's tilt might fluctuate chaotically over millions of years. Such variations could dramatically alter the planet's climate. The Moon acts as a stabilizing partner, helping keep Earth's axial tilt relatively steady. The gravitational relationship between Earth and the Moon also slowed the planet's rotation over time. Early in its history, Earth likely spun much faster than it does today, completing a full rotation in perhaps only 6 or 8 hours. Tidal interactions between the oceans and the Moon gradually transferred rotational energy away from Earth, lengthening the day to the 24 hours we experience now. This long gravitational partnership has therefore shaped the fundamental rhythms of our planet. It has influenced the length of the day, the stability of the climate, and the behavior of the oceans. In other words, the Moon is not just a distant object in the night sky. It is an integral part of Earth's history. The same gravitational bond created in that ancient collision billions of years ago continues to influence the planet today. Every tide that rises and falls along a coastline is a reminder of that deep connection between Earth and its companion world. When most people imagine the Moon influencing the oceans, the picture that comes to mind is often quite simple. It seems natural to imagine the Moon pulling the water upward, almost like a magnet lifting iron filings toward itself. It is a clear mental image, but it is not quite how tides actually work. The real mechanism is more subtle and, in many ways, more interesting. The key idea lies in something physicists call a gravitational gradient. A gravitational gradient simply means that gravity does not act equally everywhere across a large object. Instead, its strength changes with distance. The law of universal gravitation tells us that gravitational attraction weakens as distance increases. The relationship can be described by a simple statement. Gravitational force equals the gravitational constant multiplied by the mass of one object multiplied by the mass of another object, divided by the square of the distance between them. That final detail about distance is crucial. Because gravity weakens with distance, even a difference of a few thousand kilometers can change how strongly a gravitational pull is felt. On the scale of everyday human life, that difference is tiny. But on the scale of an entire planet, it becomes meaningful. Earth has a diameter of roughly 12,700 kilometers. That means the side of Earth facing the Moon is significantly closer to the Moon than the side facing away from it. The difference in distance is small compared with the total separation between Earth and the Moon, which averages around 384,000 kilometers. Yet even that modest difference is enough to create a measurable change in gravitational strength. The near side of Earth feels a slightly stronger pull from the Moon. The far side feels a slightly weaker pull. This variation across the planet is what scientists refer to as a gravitational gradient. Tidal forces arise directly from that gradient. Rather than lifting water straight upward, the Moon's gravity stretches the Earth and its oceans slightly along the line connecting the two bodies. The side of Earth closest to the Moon is pulled a little more strongly, while the opposite side is pulled slightly less. The effect is comparable to gently stretching a soft rubber ball from opposite ends. The stretching is extremely small. The solid body of the Earth itself deforms by only a few tens of centimeters under the influence of lunar tidal forces. The oceans, however, are fluid and respond more easily to these differences in gravitational acceleration. Water slowly shifts across the surface of the planet, forming broad regions where the ocean surface rises slightly and other regions where it lowers. These raised regions are known as tidal bulges. Understanding this process required far more than casual observation. It demanded careful mathematical analysis. One of the most influential figures in this effort was the French mathematician and physicist Pierre-Simon Laplace. Laplace lived during the late 1800s and early 1800s, a period when celestial mechanics was advancing rapidly. Laplace built upon the gravitational theory developed by Isaac Newton and applied it to the behavior of oceans on a rotating planet. He developed what are now known as the Laplace tidal equations. These equations describe how tidal waves propagate across the surface of a rotating sphere covered in water. Although the mathematics involved can be quite complex, the central idea is elegant. Laplace recognized that tides are not simply vertical movements of water rising and falling beneath the moon. Instead, they are enormous waves that travel through the oceans as Earth rotates. These tidal waves move through ocean basins much like slow-moving ripples, though on a planetary scale. Laplace also understood that the rotation of Earth plays a critical role in shaping these waves. As the planet spins, moving water is influenced by what physicists call the Coriolis effect, a phenomenon that causes moving fluids to curve relative to the surface of a rotating planet. The Coriolis effect was later studied in detail by the French scientist Gaspard Gustave de Coriolis, whose work helped explain the behavior of winds and ocean currents. Because of this rotational influence, tidal waves do not simply travel directly toward the moon. Instead, they follow complex paths shaped by the geometry of ocean basins and the rotation of the Earth itself. Later in the 19th century, another brilliant scientist expanded the mathematical understanding of tides. This was William Thomson, better known by his title Lord Kelvin. Kelvin made enormous contributions to many areas of physics, including thermodynamics and electrical theory, but he also spent considerable effort studying ocean tides. One of his important insights involved the idea that ocean basins can resonate with tidal forces. Resonance occurs when a system naturally oscillates at a particular frequency. A familiar example is a musical instrument. When the frequency of sound matches the natural vibration of a guitar string, the string vibrates strongly and produces a clear tone. Ocean basins can behave in a somewhat similar way. If the natural oscillation period of a basin happens to match the frequency of tidal forcing from the moon and the sun, the resulting tides can become significantly amplified. This is one reason certain places experience especially dramatic tides. The Bay of Fundy in eastern Canada is a famous example. Its shape and depth allow tidal waves to resonate strongly, producing some of the highest tides on Earth. Lord Kelvin also developed methods for predicting tides using harmonic analysis. By studying the different gravitational influences of the moon and the sun and breaking them into repeating cycles, scientists could forecast the timing and height of tides with remarkable precision. These prediction techniques became invaluable for navigation and coastal planning. Despite all the complexity involved in tidal modelling, the fundamental concept remained surprisingly simple. Tidal forces arise because gravity varies across the size of the Earth. The moon does not simply lift the oceans upward. Instead, it creates differences in gravitational acceleration between different parts of the planet. The side facing the moon experiences a slightly stronger pull. The far side experiences a slightly weaker one. This difference gently stretches the oceans along the Earth-Moon line, producing two broad tidal bulges. As Earth rotates beneath these bulges, coastlines pass through regions where the ocean surface is slightly higher and slightly lower. From the perspective of someone standing at the shore, the result is the familiar rise and fall of the sea. What appears to be a simple coastal rhythm is actually the visible outcome of a gravitational gradient acting across the entire diameter of the planet. The oceans are responding not just to the presence of the moon, but to the subtle way gravity changes from one side of Earth to the other, and that quiet difference in gravitational strength is enough to move the waters of an entire world. When we picture the moon moving around Earth, the image that often comes to mind is simple and familiar. The Earth sits in the center, solid and unmoving, while the Moon circles around it like a smaller companion tracing a steady path through space. It is an intuitive picture, and in many situations it works well enough for everyday explanation. Yet in reality, the relationship between Earth and the Moon is slightly more subtle. The Moon does not orbit a perfectly stationary Earth. Instead, both bodies move together around a shared center of mass. This point is known in physics as the barycenter. The word barycenter comes from the Greek word for weight or mass. It refers to the balance point of a system of objects, the location where their combined mass can be considered concentrated. If you imagine holding a hammer loosely in your hand, you can find its balance point by placing a finger beneath the handle and sliding it until the hammer rests without tipping. That balance position is the hammer's center of mass. Celestial systems behave in a similar way. Whenever two objects orbit each other, they both move around a shared center of mass rather than one body simply circling the other. The location of that center depends on the relative masses of the two objects. If the masses are equal, the barycenter sits halfway between them. If one object is much heavier than the other, the barycenter lies closer to the more massive body. In the case of Earth and the Moon, Earth is far more massive. Our planet has about 81 times the mass of the Moon. Because of this difference, the barycenter lies well inside Earth itself, but it does not lie exactly at Earth's center. Instead, the barycenter sits roughly 4,700 kilometers from Earth's core. That location is still within the planet, but noticeably offset from the center. This means that as the Moon travels through its orbit, Earth also performs a small motion of its own. Both bodies are constantly moving around this shared balance point. From space, the motion looks like a graceful gravitational dance. The Moon follows a wide path around the barycenter, while Earth traces a smaller circular wobble as it accompanies the Moon on that journey. This motion repeats once every 27 days, which corresponds to the Moon's orbital period relative to distant stars. The mathematics used to describe these kinds of orbital relationships belongs to a branch of physics known as celestial mechanics. One of the key figures in developing celestial mechanics was the French mathematician Joseph-Louis Lagrange. Working in the late 1700s, Lagrange expanded on the work of Isaac Newton and produced powerful mathematical methods for analyzing the motion of bodies influenced by gravity. His contributions helped scientists understand the stability of orbits, the motion of moons around planets, and the behavior of complex gravitational systems. Lagrange also identified special locations in gravitational systems now known as Lagrange points. These are regions in space where gravitational forces and orbital motion balance in such a way that objects can remain relatively stable. Today, several spacecraft operated by organizations such as the European Space Agency and NASA occupy these regions. The James Webb Space Telescope, for example, operates near a location known as the second Sun-Earth Lagrange point, nearly 1.5 million kilometers from our planet. Modern orbital mechanics research continues to build on these foundations. Scientists at NASA's Jet Propulsion Laboratory in California use highly detailed models of gravitational interactions to guide spacecraft across the solar system. When missions travel to Mars, Jupiter, or Saturn, their trajectories must account for the complex gravitational influences of multiple bodies, including the subtle effects of barycenters. These same principles also play a role in understanding tides. The shared motion of Earth and the Moon around their barycenter introduces an important effect. Because Earth is constantly circling this balance point, every location on the planet experiences a small outward tendency associated with that motion. In physics, this tendency is often described in terms of inertial effects within the rotating Earth-Moon system. When combined with the Moon's gravitational pull, this shared motion contributes to the formation of two tidal bulges rather than just one. The bulge facing the Moon forms because the Moon's gravity pulls more strongly on the near side of Earth than on the far side. Water on that side of the planet is drawn slightly toward the Moon, creating a gentle elevation in the ocean surface. At the same time, the opposite side of Earth experiences a different effect. Because Earth as a whole is orbiting the barycenter, every part of the planet experiences the same outward tendency associated with that motion. On the far side, where the Moon's gravitational pull is weaker, this outward tendency becomes relatively stronger. The result is a second tidal bulge forming on the side of Earth facing away from the Moon. The combined outcome is a pair of ocean bulges aligned roughly along the Earth-Moon line. One bulge faces the Moon, the other forms on the opposite side of the planet. As Earth rotates beneath these bulges, Coastlines pass through regions where the ocean surface is slightly elevated and slightly lowered. This rotation produces the familiar cycle of high and low tides experienced along shorelines. What might seem like a simple rise and fall of water along the beach is therefore tied to the precise mechanics of orbital motion. The oceans are responding not only to the Moon's gravity, but also to the shared movement of Earth and the Moon around their common centre of mass. It is a reminder that our planet does not move through space alone. Even in the quiet rhythm of the tides, the Earth and the Moon are moving together, bound by gravity in a partnership that has endured for billions of years. The oceans may appear calm when viewed from the shoreline, but on a planetary scale they are constantly shifting in response to gravity. The Moon, though distant, exerts a steady gravitational influence that subtly redistributes the water covering Earth's surface. This redistribution does not happen suddenly or violently. Instead, it unfolds gradually, producing broad, gentle changes in the shape of the ocean. To understand how this works, it helps to imagine Earth as a rotating sphere wrapped in a thin layer of fluid. That fluid is free to move. When forces act on it, the water can flow and adjust until a new balance is reached. The Moon's gravity is one of the forces constantly acting on that fluid shell. Because gravity weakens with distance, the side of Earth closest to the Moon experiences a slightly stronger gravitational pull than the centre of the planet. Meanwhile, the far side of Earth is slightly farther away from the Moon, and therefore experiences a slightly weaker pull. The difference between these gravitational influences may sound tiny, and in terms of raw force it truly is small. Yet when that difference acts across the enormous mass of the oceans, the result becomes visible. The water slowly shifts position. Instead of forming a sharp peak, the ocean's surface stretches gently along the direction of the Moon. The water on the near side of Earth is pulled slightly toward the Moon, creating a broad region where the ocean surface rises above its average level. This raised region is known as a tidal bulge. It is important to understand that the bulge is extremely wide and gradual. It is not a towering wave. The ocean does not suddenly heap upward into a mountain of water. Instead, the change in height typically measures only a metre or two across large areas of the open ocean. The effect is so gentle that a ship far out at sea would barely notice it. The bulge covers an enormous area, stretching across thousands of kilometres of ocean surface. If we could view the Earth from far out in space and exaggerate the effect, we would see the planet's oceans slightly elongated along the line connecting Earth and the Moon. The near side of the planet would have a subtle swelling of water pointing toward the Moon. But this is only half of the story. Perhaps the most surprising feature of tides is that a second bulge forms on the opposite side of the Earth. At first glance, this seems counterintuitive. If the Moon is pulling the oceans toward itself, why should water also pile up on the far side of the planet? The answer lies in the shared orbital motion of the Earth-Moon system. As discussed earlier, Earth and the Moon do not exist in a simple arrangement where the Moon circles a stationary Earth. Instead, both bodies orbit around a shared centre of mass known as the barycenter. This means that the entire Earth is constantly moving in a small circular path as it follows the Moon in their mutual orbit. Because every part of Earth participates in this motion, each point on the planet experiences a tendency associated with that orbital movement. In physical terms, this tendency is related to inertia, the natural resistance of objects to changes in motion. Within the rotating Earth-Moon system, this motion produces an effect that balances the Moon's gravitational pull at Earth's centre. On the near side of Earth, the Moon's gravity is slightly stronger than this balancing effect. Water there is pulled toward the Moon, forming the tidal bulge that faces it. On the far side, the situation reverses. The Moon's gravitational pull is weaker because of the greater distance. The outward tendency associated with Earth's motion around the barycenter becomes relatively stronger. As a result, water on the far side shifts outward slightly, forming a second tidal bulge pointing away from the Moon. The planet is therefore stretched gently in two directions at once. One bulge faces the Moon, the other forms directly opposite. This dual bulge structure is the defining feature of tidal motion. The solid Earth itself also experiences this stretching, though to a much smaller degree. Measurements made using sensitive instruments have shown that the ground beneath our feet rises and falls by several tens of centimetres due to tidal forces. The oceans respond much more dramatically because water flows easily. Once these bulges exist, the rotation of Earth does the rest of the work in producing the tides we experience. Earth completes one rotation relative to the distant stars in roughly 23 hours and 56 minutes. As the planet turns, different regions of its surface move through the two tidal bulges. When a coastline rotates into one of these bulges, the local sea level rises. This is what we observe as high tide. Several hours later, as Earth continues to rotate, that same coastline moves away from the bulge and into a region where the ocean surface is lower. The water level drops, producing low tide. Because there are two bulges, most coastal locations experience two high tides and two low tides during a full lunar day. A lunar day is slightly longer than an Earth day, because the Moon continues moving in its orbit while Earth rotates. The full cycle from one high tide to the next typically takes about 12 hours and 25 minutes. This subtle difference explains why the timing of tides shifts slightly from one day to the next. If you observe the ocean carefully over several days, you'll notice that high tide arrives a little later each day. That delay reflects the gradual motion of the Moon as it travels around Earth. The rising and falling of the ocean therefore reflects the precise geometry of the Earth-Moon system. Every tide along every coastline is shaped by the gravitational stretching of the planet and by Earth's steady rotation beneath the tidal bulges. It is a quiet process, unfolding continuously across the world's oceans. What feels like a simple movement of water along the shore is in fact the visible signature of celestial mechanics at work. The tidal bulges created by the Moon do not remain fixed above a single coastline. They stay roughly aligned with the Moon itself, extending outward from Earth along the line that connects the two bodies. Meanwhile, our planet continues to spin steadily beneath them. This rotation is the key to the daily rhythm of the tides. Earth rotates once relative to distant stars in about 23 hours and 56 minutes. This period is known as a sidereal day. During that time, the entire surface of the planet slowly turns beneath the gravitational pattern created by the Moon. Because of this rotation, coastlines move through the two tidal bulges that stretch along the Earth-Moon line. As a location on Earth rotates into one of these bulges, the ocean surface there is slightly elevated, producing what we call high tide. Several hours later, as Earth continues to turn, that same location rotates out of the bulge and into a region where the ocean surface is slightly lower. The water level drops, creating low tide. Eventually, the coastline continues rotating until it encounters the second tidal bulge on the opposite side of the planet. The water rises again, producing another high tide. This sequence repeats continuously. The pattern in which two high tides and two low tides occur during each day is known as a semidiurnal tidal cycle. The term comes from Latin roots meaning twice daily. Many coastal regions around the world experience this semidiurnal pattern. In these locations, the sea level rises and falls in a fairly regular rhythm that repeats twice each day. The intervals between these tides are not exactly 12 hours, however. If Earth simply rotated beneath fixed tidal bulges that never moved, the cycle would be perfectly synchronized with Earth's rotation. High tide would return at exactly the same time every day. But the Moon itself is moving. While Earth is rotating, the Moon is also traveling in its orbit around the planet. Each day, the Moon shifts slightly eastward in the sky as it continues its journey through space. The Moon completes one full orbit around Earth, relative to distant stars, in about 27 days. Because of this motion, Earth must rotate a little bit more than one full turn for the same location to line up with the Moon again. This extra rotation takes time. The result is that the tidal cycle follows the Moon rather than the Sun. The time between one high tide and the next is typically about 12 hours and 25 minutes. This interval represents half of the lunar day, which is the time it takes for a location on Earth to return to the same alignment with the Moon. A lunar day lasts about 24 hours and 50 minutes. This slightly longer cycle explains a detail that coastal observers have noticed for centuries. High tides occur later each day. If the high tide at a particular harbour occurs at 6 o'clock in the morning today, tomorrow's high tide will likely arrive around 6:25. The following day it may arrive closer to 6:50. This steady shift is the visible result of the Moon's orbital motion. The pattern has been carefully studied for generations. Long before the development of modern physics, sailors and fishermen recognized that the timing of tides followed the Moon's movements. Historical records from ports in Europe, China, and the Middle East show that mariners tracked the lunar cycle to anticipate tidal changes. In the 18th and 19th centuries, scientists began applying mathematical methods to improve tidal prediction. One important development came from the work of Lord Kelvin, also known as William Thomson, who developed harmonic analysis techniques that allowed scientists to break tidal motion into repeating cycles. These cycles correspond to the gravitational influences of the Moon, the Sun, and the rotation of Earth. Using such methods, modern oceanographers can forecast tides with remarkable accuracy. Tide tables published by organizations such as the National Oceanic and Atmospheric Administration in the United States allow sailors, fishermen, and coastal communities to know the exact timing of tides, months, or even years in advance. Behind those predictions lies a beautifully consistent astronomical rhythm. Earth rotates steadily, the Moon moves gradually along its orbit, and the oceans respond to the changing geometry between the two. The semidiurnal tidal cycle therefore emerges from a combination of two motions happening at once. The rotation of Earth carries coastlines beneath the tidal bulges, while the Moon's orbital motion slowly shifts the position of those bulges across the surface of the planet. Together, these movements produce the daily rise and fall of the sea. What appears from the shore as a gentle rhythm of water is in fact the surface expression of celestial motion. Every tide reflects the precise relationship between Earth's rotation and the Moon's journey through space. It is a reminder that even the quiet movements of the ocean are connected to the larger mechanics of the solar system. The Moon may be the primary driver of Earth's tides, but it is not acting alone. Another gravitational force is constantly at work across the oceans, and that force comes from the most massive object in our solar system, the Sun. At first, this might seem surprising. The Sun is enormously more massive than the Moon. In fact, the Sun contains more than 300,000 times the mass of Earth, and well over 27 million times the mass of the Moon. With such overwhelming mass, it might seem obvious that the Sun should dominate the tides completely. Yet in reality, the Sun's tidal influence on Earth is weaker than that of the Moon. The reason again lies in the idea of gravitational gradients. As described earlier, tides arise not simply from gravitational strength, but from differences in gravitational pull across the diameter of the Earth. The closer one object is, the greater the difference in its gravitational pull between the near side and the far side of the planet. Although the Sun is vastly more massive than the Moon, it is also vastly farther away. The average distance between Earth and the Moon is about 384,000 kilometers. By contrast, the distance between Earth and the Sun is about 150 million kilometers. In other words, the Sun is nearly 400 times farther away than the Moon. Because gravitational influence weakens rapidly with distance, the variation in the Sun's gravitational pull across Earth's diameter is smaller than the variation produced by the much closer Moon. When scientists calculate the relative strengths of these tidal effects, they find that the Moon produces roughly twice the tidal influence of the Sun. Even so, the Sun's gravitational contribution is far from insignificant. Solar gravity still affects the oceans in measurable ways, subtly modifying the height and timing of tides around the world. This means that every tide we experience on Earth is actually the result of a combined gravitational influence from both the Moon and the Sun. The oceans respond to the interaction between these two celestial forces. Sometimes the gravitational effects of the Sun and Moon reinforce each other. At other times, they partially cancel one another out. The changing geometry between these three bodies creates an additional rhythm within the tidal cycle. To understand how this works, it helps to imagine the Earth sitting between the Moon and the Sun in space. The Moon completes an orbit around Earth roughly once every 27 days. During that time, its position relative to the Sun changes steadily. Sometimes the Moon lies roughly between Earth and the Sun. At other times, Earth sits between the Moon and the Sun. There are also times when the Moon lies off to the side relative to the line connecting Earth and the Sun. These different alignments produce noticeable changes in the strength of tides. When the Earth, Moon, and Sun line up in roughly the same direction, their gravitational influences combine. The tidal forces from the Moon and the Sun act along the same line, stretching the oceans in the same general direction. When this alignment occurs, the difference between high tide and low tide becomes larger than usual. High tides rise higher than average, low tides fall lower than average. This situation produces what are known as spring tides. Despite the name, spring tides are not related to the season of spring. The term comes from an older meaning of the word spring, which refers to something that leaps or rises suddenly. Spring tides occur during two phases of the Moon. The first occurs during the new moon, when the Moon lies between Earth and the Sun. In this configuration, the gravitational forces of the Sun and Moon pull along nearly the same line. The second occurs during the full moon, when Earth lies between the Sun and the Moon. In this arrangement, the Sun and Moon still act along the same general line, though from opposite directions. In both cases, their tidal influences reinforce one another. The result is stronger tidal motion across the oceans. The water rises slightly higher and falls slightly lower than during other parts of the lunar cycle. Spring tides occur roughly twice each lunar month, appearing about every 14 days. Coastal communities have long recognized these stronger tides. Fishermen often pay attention to spring tides because the stronger water movement can influence marine life and fishing conditions. Harbour managers also monitor these periods carefully, as the increased tidal range can affect navigation in shallow waters. But the story does not end with these stronger tides. The gravitational relationship between the Sun and the Moon can also work in the opposite direction, producing tides that are noticeably weaker. When the Moon moves into positions where its gravitational pull acts at a right angle relative to the Sun's influence, the two tidal forces begin to interfere with one another rather than reinforce each other. The oceans still respond to both gravitational fields, but the combined stretching of the water becomes smaller. The difference between high tide and low tide becomes reduced. These weaker tides are known as neap tides. Understanding neap tides requires looking more closely at how the Sun and Moon can sometimes pull in different directions across the surface of the planet, and that interaction between competing gravitational influences adds yet another layer to the quiet and complex motion of Earth's oceans. The tides are shaped by more than the Moon alone. The Sun, though farther away, adds its own gravitational influence to the delicate balance of forces acting across Earth's oceans. When these two celestial bodies align in particular ways, their combined gravitational geometry changes how strongly the oceans respond. One of the most striking outcomes of this interaction is known as the spring tide. Despite the name, spring tides have nothing to do with the season of spring. The word spring in this context comes from an older English meaning, referring to something that rises, leaps, or springs upward. In tidal science, the term simply describes tides that reach unusually high levels and fall unusually low. Spring tides occur during two specific phases of the Moon. The first is the new Moon, when the Moon lies between Earth and the Sun. From our perspective on Earth, the Moon is difficult to see during this phase because its illuminated side faces away from us. The second occurs during the full moon, when Earth lies between the Sun and the Moon, allowing the Moon's sunlit surface to shine brightly in the night sky. Although these two arrangements appear very different visually, they share an important geometric feature. In both cases, the Earth, Moon, and Sun are arranged in nearly a straight line. When this alignment occurs, the gravitational forces exerted by the Moon and the Sun act along the same general direction. The tidal influence produced by the Moon combines with the tidal influence produced by the Sun. The two effects reinforce one another. The oceans are stretched more strongly along the Earth-Moon line, which means the tidal bulges become slightly larger. As Earth rotates through these enhanced bulges, the difference between high tide and low tide increases. Coastal areas experience higher than usual high tides and lower than usual low tides. This amplification does not mean the ocean suddenly rises by enormous amounts everywhere. In many open ocean regions, the change may be only a few additional centimeters. Yet in coastal locations where geography already amplifies tidal motion, the difference can become more noticeable. In some places, the stronger tidal currents associated with spring tides can dramatically alter the movement of water through narrow channels and bays. These stronger tides appear roughly twice during each lunar month. The Moon takes about 29.5 days to cycle through all its visible phases, from new moon to full moon and back again. Within that cycle, the alignments that produce spring tides occur approximately every 14 days. But the gravitational relationship between the Sun and Moon does not always reinforce tidal motion. At other times during the lunar cycle, their influences partially counteract one another. This occurs during the first quarter moon and the third quarter moon. During these phases, the Moon appears as a half-illuminated disk in the sky. More importantly, the Moon lies roughly 90 degrees away from the line connecting Earth and the Sun. In this configuration, the gravitational forces from the Sun and the Moon act at right angles relative to one another. Instead of stretching Earth's oceans along the same line, their tidal influences pull in different directions. The result is a partial cancellation of tidal forces. The tidal bulges created by the Moon still exist, but the Sun's gravitational influence slightly reduces their height. When this happens, the difference between high tide and low tide becomes smaller than usual, These weaker tides are known as neap tides. During a neap tide cycle, high tides do not rise as high, and low tides do not fall as low. The ocean surface still moves up and down with the same general rhythm, but the range between the two extremes becomes noticeably reduced. Just like spring tides, neap tides occur on a repeating schedule tied to the lunar cycle. They appear approximately halfway between the stronger spring tides, about 7 days after a full moon and 7 days after a new moon. This alternating sequence creates a rhythmic pattern in the oceans. Roughly every 2 weeks, the tidal range grows stronger during spring tides, then weakens again during neap tides. Long before modern science explained the underlying physics, coastal communities were already familiar with this pattern. Sailors, fishermen, and harbour workers carefully observed the changing strength of tides. In many maritime cultures, knowledge of the lunar cycle was considered essential for safe navigation. Ancient navigators in regions such as the Mediterranean Sea and the North Atlantic tracked the phases of the moon to anticipate when the strongest tides would occur. Knowing when the water would rise or fall could determine whether a ship could safely enter a shallow harbour or cross a tidal channel. Historical tide tables from the 18th and 19th centuries reveal how carefully mariners studied these cycles. British naval officers, Dutch harbour engineers, and French coastal surveyors all contributed to early efforts to predict tidal patterns. One of the most important scientific advances in tidal prediction came from the work of Lord Kelvin in the 19th century. His mathematical approach to harmonic analysis allowed scientists to break tidal motion into multiple repeating components associated with the gravitational influences of the moon and the sun. These techniques laid the foundation for modern tidal forecasting systems. At its core, the alternating pattern of spring and neap tides reveals something fundamental about the nature of gravity. Gravity does not act in isolation. The oceans respond to the combined gravitational geometry of multiple celestial bodies. The position of the moon relative to the sun determines whether their tidal influences strengthen each other or partially cancel out. The ocean is therefore responding not only to individual objects in space, but to the precise angles between them. In this sense, tides are a visible expression of celestial geometry. The alignment of Earth, the Moon, and the Sun shapes the movement of water across the entire planet. The oceans rise and fall in response to these changing spatial relationships, quietly reflecting the larger architecture of the solar system. What appears from the shoreline as a simple cycle of water is in fact the outcome of gravitational forces interacting across millions of kilometers of space. If the Moon pulls on the oceans everywhere, it might seem reasonable to expect tides to behave the same way along every coastline. One might imagine the ocean rising and falling by the same amount across the entire planet. But the reality is far more varied. In some locations, the difference between high tide and low tide may be only a few tens of centimeters. In others, the ocean can rise and fall by several meters. In the most extreme places, the vertical change in sea level can exceed 15 meters. The Moon's gravitational influence is nearly the same across all of Earth's oceans, so the reason for these dramatic differences must lie somewhere else. The explanation lies in geography. More specifically, it lies in the shapes and sizes of the ocean basins themselves. Earth's oceans are not simple open bowls filled with water. They are complex landscapes shaped by continents, underwater ridges, seafloor mountains, and deep trenches. These features influence how tidal waves travel across the planet. To understand this idea, it helps to think of tides not simply as water rising and falling in place, but as enormous waves moving through the oceans. These waves are extremely long compared with familiar ocean waves created by wind. A typical wind-driven wave might be a few tens of meters long from crest to crest. A tidal wave, by contrast, can stretch across entire ocean basins, sometimes spanning thousands of kilometers. Because tidal waves are so large, their movement interacts strongly with the shape of the ocean basins through which they travel. This is where the concept of tidal resonance becomes important. Resonance is a physical phenomenon that occurs when a system naturally oscillates at a particular frequency. If energy is supplied to the system at that same frequency, the oscillation grows stronger. A familiar example can be found in musical instruments. When the sound waves produced by a violin match the natural vibration frequency of the instrument's wooden body, the sound becomes amplified and rich. Ocean basins can behave in a similar way. If the natural oscillation period of an ocean basin happens to match the frequency of the tidal forcing produced by the Moon and the Sun, the tidal waves within that basin can become amplified. This idea was explored in detail by the British oceanographer Joseph Proudman during the early 20th century. Proudman was one of the founders of modern physical oceanography, and his work helped establish how the shape and depth of ocean basins influence tidal motion. Working with colleagues at institutions such as the University of Liverpool's Tidal Institute, Proudman developed mathematical models describing how tidal waves propagate through shallow seas and enclosed basins. His research showed that when the natural period of oscillation in a basin closely matches the tidal forcing period of roughly 12 hours and 25 minutes, resonance can occur. When that happens, the tidal range can grow significantly larger. One of the most famous examples of tidal resonance occurs in the Bay of Fundy. The Bay of Fundy lies along the eastern coast of Canada, between the provinces of New Brunswick and Nova Scotia. It forms a long, narrowing inlet connected to the Atlantic Ocean. The shape of this bay turns out to be almost perfectly suited for tidal amplification. The natural oscillation period of water moving within the bay is close to the same period as the dominant tidal cycle produced by the moon. As tidal waves enter the bay, the water begins to slosh back and forth in resonance with the incoming tides. Each cycle adds energy to the motion. The result is an extraordinary amplification of tidal height. In some areas of the Bay of Fundy, the difference between high tide and low tide can exceed 16 meters. This makes it one of the largest tidal ranges anywhere on Earth. During low tide, vast areas of seabed become exposed, revealing mudflats that stretch for kilometers. Fishing boats may sit tilted on the muddy ground, waiting patiently for the sea to return. Several hours later, the incoming tide floods back into the bay, lifting the water level dramatically and carrying those same boats high above the previously exposed seafloor. The transformation can be astonishing to witness. Resonance is not the only factor shaping tides, however. The rotation of Earth also influences how tidal waves travel through ocean basins. When large masses of water move across a rotating planet, their motion is affected by the Coriolis effect. This phenomenon causes moving fluids to curve relative to the surface of the Earth. Because of this effect, tidal waves often follow curved paths as they move through the oceans. One important class of tidal waves is known as Kelvin waves, named after the 19th century physicist William Thomson, better known as Lord Kelvin. Kelvin studied how waves behave in rotating fluids and discovered that certain waves can travel along coastlines or boundaries while maintaining a consistent structure. A Kelvin wave moves with the coastline on one side and the open ocean on the other. As it travels, the rotation of Earth helps keep the wave trapped against the boundary. In tidal systems, Kelvin waves allow tidal energy to circulate around ocean basins in large rotating patterns. In some parts of the world, these rotating tidal systems create regions known as amphidromic points. At these locations, the tidal range becomes extremely small, sometimes only a few centimeters. Around an amphidromic point, tidal waves rotate in a circular pattern across the surrounding ocean basin. Maps of global tides reveal several such systems in the world's oceans, including regions in the North Sea, the South Pacific, and parts of the Indian Ocean. This means that tides are not simply rising and falling everywhere at the same time. Instead, tidal waves move across the oceans in complex patterns shaped by geography, basin resonance, and planetary rotation. The result is a rich variety of tidal behaviors around the world. Some coastlines experience strong semidiurnal tides with two large highs and lows each day. Others display mixed patterns where the heights of successive tides differ noticeably. Still others experience relatively small tidal ranges because the local geography prevents tidal waves from building significant amplitude. Despite these differences, all of these patterns ultimately trace back to the same gravitational forces acting across the planet. The moon and the sun provide the energy that drives the tides. The oceans themselves determine how that energy is expressed. The geography of Earth transforms a single gravitational influence into a complex and fascinating tapestry of tidal motion across the globe. The oceans do not simply sit still while tides pass through them. Instead, they are part of a dynamic system shaped by several powerful influences working together. Gravity provides the driving force behind tides, but the motion of the water itself is also shaped by Earth's rotation, and by the complex circulation patterns that move heat and energy through the seas. One of the most important physical effects produced by Earth's rotation is known as the Coriolis effect. This effect was first described mathematically in 1835 by the French engineer and scientist Gaspard Gustave de Coriolis. While studying the motion of rotating mechanical systems, Coriolis realized that objects moving across a rotating surface appear to follow curved paths rather than straight lines. Although Coriolis originally developed his mathematics for industrial machines, the principle applies equally well to the rotating Earth. Because our planet spins once every 24 hours, anything moving across its surface experiences a subtle deflection. In the northern hemisphere, moving objects tend to curve toward the right relative to their direction of motion. In the southern hemisphere, they curve toward the left. This effect is small at everyday scales, but it becomes very important when dealing with large masses of air or water traveling across thousands of kilometers. Meteorologists rely on the Coriolis effect to explain the rotation of hurricanes and large atmospheric circulation systems. Oceanographers use the same principle to understand how ocean currents and tidal waves move across the seas. When tidal waves propagate through the oceans, they are not moving across a stationary surface. They are moving across a rotating planet. As a result, the Coriolis effect gently alters their paths. Instead of travelling in simple straight lines directly toward and away from the moon, tidal waves often curve and circulate within the boundaries of ocean basins. This interaction between tidal motion and planetary rotation produces one of the most fascinating patterns in ocean dynamics. These patterns are known as amphidromic systems. An amphidromic system is a rotating tidal pattern that forms within an ocean basin. At the centre of this system lies a point called an amphidromic point, where the tidal range is extremely small. In some cases, the change in sea level near an amphidromic point may be only a few centimetres. To someone standing there, the ocean would appear almost motionless in terms of tidal rise and fall. Yet surrounding that quiet centre, tidal waves rotate in broad circular patterns across the basin. Imagine placing a small pebble in the centre of a calm pond and watching ripples move outward in rings. Amphidromic systems behave somewhat differently, but the idea of circular motion around a central point provides a useful mental picture. As tidal waves travel through the basin, they rotate around the amphidromic point, with the height of the tide increasing as one moves farther from the centre. This means that coastal regions located along the outer edges of an amphidromic system often experience much larger tidal ranges than locations near the centre. Several such systems exist throughout the world's oceans. One well-studied example lies in the North Sea between the United Kingdom and continental Europe. Another can be found in the South Pacific Ocean. Similar rotating tidal systems occur in the Indian Ocean and in parts of the Atlantic. The existence of these patterns reveals just how strongly Earth's rotation shapes tidal motion. Scientists began mapping these tidal systems during the 19th and early 20th centuries as measurements of sea level became more precise. Later work by oceanographers helped explain the physics behind these rotating waves. One of the influential figures in modern physical oceanography was the American scientist Henry Stommel. Working during the middle of the 20th century, Stommel made major contributions to understanding ocean circulation. He developed theoretical models describing how large-scale currents form and how water moves through the global ocean system. Stommel showed that the interaction between Earth's rotation, ocean basin geometry, and fluid dynamics plays a crucial role in shaping the movement of seawater. His research helped clarify how tides interact with other ocean processes, including the massive circulation systems that transport heat around the planet. These circulation systems form part of what scientists call the global thermohaline circulation. The name comes from the two main factors driving the flow of deep ocean water: temperature and salinity. Cold, salty water tends to sink because it is denser than warm water. In polar regions, where seawater becomes both cold and salty as ice forms, large masses of water sink toward the ocean floor. These deep currents slowly travel through the world's oceans, eventually rising again in other regions. The entire circulation pattern acts like a planetary conveyor belt, redistributing heat from the tropics toward the poles. Tidal motion interacts with this global circulation in several ways. As tidal waves move across the seafloor, they generate turbulence and mixing within the water column. This mixing helps transport nutrients and oxygen through the ocean depths, influencing marine ecosystems. In certain narrow passages and continental shelf regions, tidal currents can become particularly strong. In places such as the Strait of Messina between Italy and Sicily, tidal flows produce swirling vortices and powerful currents that have fascinated observers for centuries. Even in the open ocean, where tidal height changes may be modest, tidal currents still play an important role in redistributing energy through the water. The combination of gravitational forces, Earth's rotation, and ocean circulation creates a dynamic environment where water is constantly in motion. Tides, currents, and planetary rotation interact in ways that produce complex patterns across the world's oceans. Yet despite this complexity, the underlying driver remains the same. The Moon and the Sun provide the gravitational energy that sets the oceans in motion. Earth's rotation and the structure of the ocean basins shape how that energy moves through the water. Together they form a vast and interconnected system, where even the quiet rise and fall of the sea reflects the deeper physics of a rotating planet covered in moving water. The tides may appear gentle and repetitive, but they are part of a long exchange of energy between Earth and the Moon. Every rise and fall of the ocean involves motion, and whenever motion occurs in a physical system, some energy is inevitably transformed and dissipated. In the case of tides, that transformation occurs through a process known as tidal friction. Tidal friction arises because the oceans do not move freely without resistance. As tidal bulges shift across the planet, seawater flows over the seafloor, through narrow straits, around continents, and across submerged ridges and mountains. These movements create turbulence and drag. Water rubs against the rough surface of the ocean floor. It collides with coastlines and circulates through shallow continental shelves. In these regions, the motion of water is slowed slightly by friction. This friction converts a small portion of tidal energy into heat. The amount of heat generated is not large enough to noticeably warm the oceans, but the energy loss has an important consequence for the dynamics of the Earth-Moon system. Because tidal motion is powered by Earth's rotation relative to the Moon, any loss of tidal energy must ultimately come from the rotational energy of the planet itself. In other words, the tides are gradually slowing the spin of the Earth. This idea was explored in detail during the 19th century by the British scientist George Darwin, the son of the famous naturalist Charles Darwin. George Darwin was a mathematician and astronomer who devoted much of his career to studying tidal forces and the long-term evolution of planetary systems. Using Newtonian mechanics, he developed models describing how tidal interactions transfer angular momentum between orbiting bodies. Darwin realized that the tidal bulges created by the Moon are not perfectly aligned with the Earth-Moon line. Because Earth rotates more quickly than the Moon orbits, the tidal bulges are carried slightly ahead of the Moon's position. In effect, Earth's rotation drags the ocean bulges forward. This slight offset creates a gravitational interaction between the bulges and the Moon itself. The mass of the tidal bulges exerts a small gravitational pull on the Moon, gently tugging it forward along its orbital path. This forward pull adds energy to the Moon's orbit. At the same time, the energy required to produce that orbital change comes from the rotational energy of the Earth. As a result, Earth's rotation gradually slows while the Moon moves slightly farther away. George Darwin's calculations suggested that this process had been operating for billions of years. When the Moon first formed after the giant impact event that created it, it likely orbited much closer to Earth than it does today. Over immense spans of time, tidal friction steadily transferred energy from Earth's spin into the Moon's orbit. This caused the Moon's orbital distance to grow. For many decades, Darwin's theory remained largely theoretical, because there was no direct way to measure the Moon's slow outward motion with sufficient precision. That situation changed during the 20th century, with the arrival of human space exploration. During the Apollo missions between 1969 and 1972, astronauts placed several special instruments on the lunar surface. Among these devices were arrays of mirrors known as retroreflectors. These reflectors were designed to bounce laser light directly back toward its source, no matter the angle at which the light arrives. Scientists on Earth use powerful lasers to send short pulses of light toward these reflectors on the Moon. The light travels to the Moon, strikes the mirrors, and returns to Earth. By measuring the time it takes for the light to complete this round trip, scientists can calculate the distance to the Moon with extraordinary accuracy. Because light travels at a known speed of about 300,000 kilometers per second, even tiny differences in travel time reveal extremely precise changes in distance. The technique is known as lunar laser ranging. Experiments conducted by research groups at institutions such as the Jet Propulsion Laboratory and the Apache Point Observatory in New Mexico have used lunar laser ranging to track the Moon's orbit for decades. The results have confirmed Darwin's prediction. Measurements show that the Moon is slowly drifting away from Earth at a rate of about 3.8 centimeters each year. That distance may sound insignificant. It is roughly the width of a small coin, or about the speed at which human fingernails grow. Yet over geological timescales, the effect becomes substantial. Over 1 million years, the Moon moves roughly 38 kilometers farther away. Over 100 million years, the distance increases by several thousand kilometers. This gradual separation has already changed the character of Earth's tides compared with the distant past. When the Moon was closer to Earth billions of years ago, tidal forces were far stronger. The tidal bulges would have been larger, and the difference between high tide and low tide could have been much greater than what we observe today. The stronger tides may have influenced early coastal environments, possibly playing a role in the development of tidal pools where early forms of life evolved. At the same time, Earth's rotation was faster. Geological evidence suggests that hundreds of millions of years ago, a full day on Earth may have lasted only about 22 hours. In the distant past, the day may have been even shorter. Tidal friction has been gradually lengthening the day ever since. Even today, Earth's rotation continues to slow by a tiny amount each century. The change is extremely small, measured in milliseconds, but over long timescales it accumulates. This means the relationship between Earth and the Moon is not static. It is evolving. The tides we observe today represent just one moment in a very long story of gravitational interaction. Over billions of years, the Earth-Moon system has slowly adjusted itself through the steady transfer of energy between rotation and orbit. The quiet rise and fall of the ocean is therefore part of a much larger process. Every tide carries away a tiny fraction of Earth's rotational energy. Every tidal cycle nudges the Moon slightly farther into space, and through this slow exchange, the Earth and the Moon continue their gravitational partnership, changing together over the immense timescales of planetary history. The tides we experience today feel familiar and predictable, yet they are only the latest chapter in a story that stretches far back into Earth's geological past. The Moon has been influencing our oceans for billions of years, and the record of that influence has been quietly preserved in the rocks beneath our feet. To see this evidence, scientists turn to a remarkable geological structure known as a tidal rhythmite. A tidal rhythmite is a layered sedimentary formation created by the repeated rise and fall of ancient tides. In coastal environments such as tidal flats or shallow estuaries, water flowing in and out with each tide carries fine particles of sand, silt, and clay. As the water slows during slack tide, these particles settle onto the seafloor in thin layers. When the tide returns, another layer forms. Over time, the steady alternation between incoming and outgoing tides produces a sequence of fine sediment bands stacked on top of one another. Each layer represents a specific stage in the tidal cycle. These deposits can accumulate year after year, eventually becoming compacted and preserved as solid rock. When geologists examine such formations millions of years later, they can sometimes see the repeating patterns that record the rhythm of ancient tides. Under careful analysis, these patterns reveal far more than simply the presence of tides in the past. The spacing and grouping of layers often reflect multiple cycles occurring simultaneously. Some layers correspond to daily tides, while others reveal patterns associated with the roughly 2-week cycle between spring tides and neap tides. Still others preserve evidence of seasonal variations. By measuring these repeating patterns, scientists can reconstruct how often tides occurred in the distant past. One of the most famous tidal rhythmite deposits lies in the Elatina Formation of South Australia. This rock formation dates back roughly 620 million years to the late Precambrian era. When geologists studied the finely layered sediments preserved there, they discovered a remarkable pattern. The number of tidal layers within each repeating sequence suggested that the length of a day was significantly shorter at that time. Detailed analysis of the Elatina rhythmites indicates that there were about 400 days in a year during that period of Earth's history. If the number of days per year was larger while the length of the year remained roughly the same, it means each day must have been shorter. The calculations suggest that a single day may have lasted only about 21 hours. This evidence aligns beautifully with the predictions made by tidal evolution theory. If tidal friction gradually slows Earth's rotation over time, then the planet must have rotated more quickly in the distant past. Tidal rhythmites therefore provide a geological record confirming that Earth's rotation has been slowing for hundreds of millions of years. The rocks themselves are quietly preserving the rhythm of ancient oceans. Another remarkable source of evidence comes not from sedimentary rock but from the remains of living organisms. Certain types of marine organisms grow in ways that record the passage of time with surprising precision. One of the most useful examples comes from fossil corals. Many coral species grow by depositing thin layers of calcium carbonate to form their skeletons. These layers often develop daily growth increments similar to the growth ring seen in trees. Within those daily layers, scientists can sometimes detect larger patterns that correspond to seasonal cycles. By counting how many daily growth bands occur within a single annual cycle, researchers can determine how many days existed in a year at the time the coral was alive. Studies of fossil coral from the Devonian period, roughly 400 million years ago, have revealed that Earth once experienced around 400 days per year. This again implies that each day must have been shorter than the 24 hours we experience today. Some fossil coral studies suggest that a day during the Devonian period lasted about 22 hours. This method of measuring ancient day length has been refined through careful work by paleontologists and geophysicists. Researchers examine microscopic growth patterns preserved within fossilized coral skeletons and compare them with modern coral growth patterns to ensure the interpretation is accurate. These biological records provide an independent confirmation of the geological evidence found in tidal rhythmites. Both sources point to the same conclusion. Earth's rotation has been gradually slowing over immense spans of time. The slowing occurs because tidal friction continuously removes a small amount of rotational energy from the planet and transfers it into the Moon's orbit. In effect, the tides are acting like a very gentle brake on Earth's rotation. The process unfolds so slowly that it is invisible within a single human lifetime. Yet over hundreds of millions of years, the cumulative effect becomes unmistakable. The rocks and fossils preserved across Earth's surface quietly document these changes. They reveal a planet whose day length has slowly increased while the Moon has drifted farther away. When geologists examine ancient tidal deposits, they are not only studying sediment layers, they are reading a physical record of celestial mechanics. Each thin band of sediment tells part of the story of how Earth and the Moon have interacted through time. These records remind us that tides are not merely coastal events. They are part of a planetary process that has been shaping Earth for billions of years. The oceans, the Moon, and the rotation of the planet are all linked through the steady exchange of gravitational energy. Even long after the tides themselves have vanished from view, their imprint remains etched in the rocks. Through those ancient patterns, the history of Earth's changing rotation continues to speak across the vast expanse of geological time. The tides of Earth may feel like a uniquely familiar feature of our planet, yet tidal forces are not exclusive to Earth or even to oceans. The same gravitational interactions that gently raise and lower our seas operate throughout the solar system, shaping the behavior of planets, moons, and even the internal structure of distant worlds. Wherever one celestial body orbits another, tidal forces are at work. Sometimes those forces produce visible motion, such as the ocean tides we experience on Earth. In other cases, the consequences are far more dramatic. Entire moons can be stretched, heated, and reshaped by tidal interactions. One of the most striking examples occurs around the giant planet Jupiter. Jupiter possesses a powerful gravitational field, far stronger than Earth's, because it is the most massive planet in the solar system. Orbiting around it are dozens of moons, several of which experience intense tidal forces due to Jupiter's enormous gravity. Among these moons, one stands out as the most extreme example of tidal activity. This moon is called Io. Io was first observed by Galileo Galilei in the year 1610, when he discovered the 4 largest moons of Jupiter through his telescope. For centuries it appeared as a simple point of light. Only in the 20th century did scientists begin to understand how extraordinary Io truly is. Io is roughly the size of Earth's moon, but its surface is completely different. Instead of being quiet and heavily cratered, Io is the most volcanically active body known in the entire solar system. Hundreds of volcanoes erupt across its surface. Some of these eruptions send plumes of sulfur and ash hundreds of kilometers above the moon's surface. The source of this extreme geological activity is tidal heating. Tidal heating occurs when gravitational forces repeatedly stretch and compress a celestial body as it moves through an orbit. In Io's case, Jupiter's gravity pulls strongly on the moon, distorting its shape. However, Io does not orbit Jupiter in a perfectly circular path. Its orbit is slightly elliptical, meaning the distance between Io and Jupiter changes slightly during each orbit. As Io moves closer to Jupiter, the gravitational pull increases. When it moves slightly farther away, the pull decreases. This changing gravitational force causes Io's interior to flex continuously. Imagine repeatedly bending a metal wire back and forth. Eventually the wire warms up because the repeated motion converts mechanical energy into heat. Something similar happens inside Io. The constant flexing of the Moon's interior generates enormous heat within its rocky mantle. That heat melts rock beneath the surface and drives the powerful volcanic activity observed there. Much of our understanding of tidal heating on Io comes from the work of planetary scientists such as Stanton Peele. During the 1970s, Peele and his colleagues developed theoretical models predicting that tidal forces could generate intense internal heating within moons orbiting giant planets. Their predictions were dramatically confirmed when the Voyager spacecraft flew past Jupiter in 1979 and photographed Io's erupting volcanoes. Tidal forces are also believed to shape several other moons in the outer solar system. Two of the most intriguing examples are Europa, another moon of Jupiter, and Enceladus, a moon of Saturn. Europa has a smooth, icy surface crisscrossed by long fractures and ridges. Beneath that frozen shell, scientists believe a global ocean of liquid water may exist. Evidence for this ocean comes from multiple spacecraft observations, including measurements made by NASA's Galileo mission during the 1990s. The gravitational influence of Jupiter appears to flex Europa's interior, generating enough heat to maintain liquid water beneath the ice. Tidal heating may therefore help sustain one of the most promising environments for extraterrestrial life in our solar system. Enceladus provides another fascinating example. This small moon of Saturn was once thought to be geologically inactive. However, observations made by the Cassini spacecraft revealed enormous geysers of water vapor erupting from cracks near the moon's south pole. These plumes contain water, ice particles, and organic molecules. Scientists believe that tidal heating produced by Saturn's gravitational pull keeps a subsurface ocean beneath Enceladus warm enough to remain liquid. The geysers erupt through fractures in the icy crust, sending material into space. Once again, tidal forces are acting as a source of energy within a distant world. Another consequence of tidal forces can be seen in the way many moons rotate. Most large moons in the solar system are tidally locked to the planets they orbit. Tidal locking means that the same side of the moon always faces its parent planet. Earth's moon is a familiar example. No matter when we observe it from Earth, we always see the same hemisphere. The opposite side, often called the far side, remained unseen by human eyes until spacecraft first photographed it during the 1950s. Tidal locking occurs because tidal forces gradually slow the rotation of a moon until its rotational period matches its orbital period. Once these two periods become synchronized, the same face remains pointed toward the planet. The mathematical explanation for this phenomenon was explored in detail by the Italian mathematician Giuseppe Colombo. Colombo's work helped clarify how tidal interactions can produce stable rotational states in orbiting bodies. Further research into tidal evolution was carried out by planetary dynamicists such as Peter Goldreich. Goldreich studied how tidal forces influence the long-term stability of planetary systems, including the gradual transfer of angular momentum between rotating bodies and their orbits. His work provided important insights into how moons migrate outward over time and how rotational states evolve under tidal forces. Across the solar system, these interactions reveal that tides are far more than coastal events. They are a universal consequence of gravity acting across extended bodies. Whether raising Earth's oceans, heating the interior of distant moons, or locking the rotation of satellites, tidal forces quietly shape the evolution of planetary systems. In this sense, the tides we observe along our own coastlines are just one small expression of a much broader cosmic phenomenon. The same gravitational principles that move Earth's oceans are also reshaping moons, warming hidden oceans beneath ice, and sculpting the architecture of worlds throughout the solar system. The tides we experience along Earth's coastlines are often thought of as a local phenomenon, something belonging specifically to our oceans and our moon. Yet the physics behind tides extends far beyond Earth. The same gravitational interactions that move seawater here operate throughout the universe, wherever massive bodies influence one another. Tidal forces are not unique to oceans. They arise whenever gravity acts across the diameter of an extended object. Any time one celestial body pulls more strongly on one side of another body than the other side, the object experiences tidal stretching. The result may be moving oceans, deforming crusts, heated interiors, or altered orbits. Once this principle is understood, it becomes clear that tides are not simply an earthly curiosity. They are a universal consequence of gravity. Across the solar system, tidal interactions shape the behavior of planets and moons. On Earth, they raise the oceans. On other worlds, they can fracture ice crusts, power volcanic eruptions, and even determine how quickly a planet rotates. But tidal forces become even more interesting when we look beyond our own solar system to the growing collection of planets orbiting distant stars. These worlds, known as exoplanets, have become one of the most active areas of modern astronomy. Since the first confirmed detection of an exoplanet orbiting a Sun-like star in the year 1995, astronomers have discovered thousands of such worlds. Many of these planets orbit extremely close to their host stars. In some cases, the distance between the planet and the star is only a few million kilometers, far closer than Mercury's orbit around our Sun. At such distances, tidal forces become extremely powerful. When a planet orbits close to a star, the gravitational gradient across the planet can be strong enough to dramatically alter its rotation. Over time, tidal forces tend to slow the planet's rotation until it becomes tidally locked. Tidal locking means that the same side of the planet always faces its star. A familiar example already exists within our own sky. Earth's moon is tidally locked to Earth, which is why we always see the same lunar hemisphere. But for exoplanets orbiting close to their stars, tidal locking may be the rule rather than the exception. This possibility has important consequences for planetary climate. Astrophysicist Sarah Seeger, who has conducted extensive research on exoplanet atmospheres and habitability at institutions including the Massachusetts Institute of Technology, has explored how tidal locking might influence the environments of distant planets. If a planet becomes tidally locked to its star, one hemisphere permanently faces the star while the other remains in perpetual darkness. This creates a world with a constant day side and a constant night side. At first glance, such a situation might seem hostile to life. The day side could become extremely hot while the night side could freeze. However, climate models developed by researchers studying exoplanet atmospheres suggest that a sufficiently thick atmosphere or a global ocean could redistribute heat between the two hemispheres. Air currents and ocean circulation might transport energy from the day side to the night side, creating regions where temperatures remain stable enough for liquid water to exist. These ideas have led scientists to consider an expanded concept of planetary habitability. Traditionally, astronomers have focused on what is called the habitable zone around a star. This is the region where a planet receives just the right amount of stellar energy to maintain liquid water on its surface. But tidal forces add another dimension to this picture. In some planetary systems, tidal heating generated by gravitational interactions could provide an additional source of energy. Even if a planet or moon lies outside the traditional habitable zone, tidal heating might warm its interior enough to maintain liquid water beneath its surface. Scientists sometimes refer to these environments as tidal habitable zones. A moon orbiting a giant planet could experience continuous tidal flexing that produces internal heat. That heat might melt subsurface ice, creating oceans hidden beneath frozen crusts. Europa and Enceladus within our own solar system already provide examples of how this process might work. Astronomers studying exoplanet systems are now searching for similar possibilities on worlds orbiting distant stars. Observational research conducted by institutions such as the Harvard-Smithsonian Center for Astrophysics and other international research groups is helping scientists understand how tidal forces shape planetary systems beyond our own. Using telescopes both on Earth and in space, astronomers measure tiny variations in starlight as planets pass in front of their host stars. These measurements reveal the size, mass, and orbital characteristics of distant worlds. By analysing those orbital properties, scientists can estimate how strong tidal forces might be within those systems. Some planets appear to experience extreme tidal interactions that may generate intense internal heating. Others may have become tidally locked long ago, permanently presenting one hemisphere toward their star. In some cases, tidal forces may even influence whether a planet retains its atmosphere. If a planet orbits extremely close to its star, tidal heating could drive geological activity that releases gases into the atmosphere. Alternatively, strong tidal stresses might gradually strip an atmosphere away. These processes illustrate how tidal physics shapes not only oceans but entire planetary environments. The concept of tides therefore connects a simple coastal observation with the broader workings of gravity across the cosmos. The same physical principles that raise seawater along a beach can also warm the interior of distant moons, reshape the rotation of planets, and influence the climates of worlds orbiting other stars. Tides remind us that gravity is not merely a force that holds objects together. It is an interaction that constantly redistributes energy throughout the universe. Whenever massive bodies orbit one another, tidal forces quietly reshape their motion, their internal structure, and sometimes even their potential to support life. The gentle rise and fall of Earth's oceans is therefore just one expression of a much larger cosmic phenomenon. Across the universe, countless worlds are being stretched, heated, and reshaped by gravity. And every one of those distant tides obeys the same fundamental laws that move the waters of our own planet.